Welcome students to this next session on industrial metallurgy. The module is alloy systems. Uh, in this session number 11, these are the contents that we shall discuss with you. Okay, so in the last session, we finished with the unary equilibrium diagrams. Now we start with what are called binary phase diagrams or binary equilibrium diagrams. So binary equilibrium diagrams are phase diagrams which are drawn for two component systems. So uh, in other words, binary phase diagrams are diagrams which would be drawn for binary alloys. Now in a two component system, you see binary equilibrium diagram would mean graphical representation of what different phases are seen in a binary alloy under different conditions of pressure, temperature, and composition. Because composition also now is a variable, because the two components that have gone into to form the binary alloy can be mixed in infinite uh, proportions, weight proportions, and so composition is also a variable. But fortunately, for most of the binary alloys, when they are processed, the pressure conditions remain constant at atmospheric pressure conditions. So pressure is constant at 1 atm. So we are left with only two variables, one temperature and the other composition. So binary phase diagram shows to you that for a given binary alloy under different conditions of pressure, temperature and composition, what different phases would be observed, right? Then before actually we proceed with binary equilibrium diagrams, there are a couple of things which must be clear to us. The first is that why do we need to form an alloy? What's the problem with the metals? You see, when extractive metallurgy has been done and you have obtained the metals in their purest form, most of the metals would be good in some of the physical properties, like corrosion resistance might be very good, or ductility might be very good, luster may be very good, electrical heat conductivity might be very good. But when it comes to engineering properties like strength, hardness, impact strength, resilience, etc., etc., metals do not show up very well. So the properties of the metals need to be changed, need to be improved upon, and one of the methods of doing that is through alloying. So the main need of forming an alloy is to improve the mechanical properties of a metal system. And how do we define an alloy? An alloy is a material system which essentially would have metallic properties. If you form a material system with improved properties but that's not having metallic characteristics, like metallic bonding is not there, luster is not there, uh, then it's not an alloy. It may be a material system with improved properties, but then it's not an alloy. So alloy is a material system which essentially has to have metallic properties, and it is formed by the intimate combination of a metal. So at least one metal has to be there, with one or more than one metals and or non-metals. And for these conditions to be met, when you look into a alloy system, it should be the metal atoms which should be dominating in composition. It should be the metallic bonding. Any type of bonding can be there in a alloy system, but the most domineering type of bonding has to be metallic bonding. So if in composition the metal atoms are in maximum friction, and in bonding if it's the metallic bonding which is most uh, prevalent, then the type of system that would get formed is called an alloy system. Steels and cast irons are one of the most commonly used examples of alloys. Steels and cast irons have got principally iron in them, but the main alloying element is carbon. Similarly, brass is an alloy of copper and zinc. Bronze is an alloy of copper with tin and other elements apart from zinc. So all these are examples of alloys. What's the general procedure of alloying? There are many methods which are used for forming alloys. sintering is there, sublimation is there, but the most important method is simple melting. And what do we do in here? We take all the constituents. The constituent which has got the highest melting point is melted first in the furnace, and then the other constituents are added to it. We stir this mixture and we form a homogeneous liquid solution. Mind it, if a homogeneous liquid solution of the constituent elements do not get formed, generally a good commercially useful alloy will not get formed. Yes, there are exceptions to it. There are certain exceptions, like a Babbitt alloy is in which the lead remains undissolved, but in 99.9% cases, if a good alloy is getting formed, the first condition that the constituent elements have met is that they have formed a homogeneous liquid solution. And students, now we come to one of the classifications of alloy systems, which is done on the basis of the properties or the characteristics which are shown by the phases. Okay, now in other words, we can say that what is the classification or categories of phases if we try to classify them on the basis of the characteristics or the properties that they show. If you remember, in one of the earlier sessions we had done classification of phases, but that was on the basis of equilibrium, and there we had said there are three classes of phases: equilibrium phase, metastable phase, non-equilibrium phase. Here we are doing classification of phases, and this classification is on the basis of the properties, the characteristics which the phases show. There are two main types of phases on this basis. One type is called the solid solutions, the other is called the intermediate phase, right? So solid solution is one type of phases and intermediate phases are of another type. This first category, solid solution, has got further two types: interstitial solid solutions and substitutional solid solutions. And this intermediate phase type has got three types. One are called interstitial compounds or size factor compounds. The other are called Hume-Rothery compounds or electron compounds. And the last category under intermediate phases is intermetallic compounds, or what are also called the valency compounds. Okay. Now we have to see what is meant by a solid solution. But you mind it, if you are saying that an alloy system has got formed, one of the phases that ought to must be existing in the alloy system is a solid solution. You cannot have an alloy in which there is no solid solution. You may have an alloy which is only having a solid solution or more than one type of solid solutions. That means you might not have this type of a phase. But in an alloy system, it is not possible that you have only this type of a phase and this is not there. In other words, this phase is only a byproduct of this. This may be there or this may not be there. If this is forming a solid solution, there is no byproduct, you will only see a solid solution or some solid solutions in the alloy. And if it contains excess of solute which cannot get dissolved in the solid solution, then this, under those conditions, this second type of phase will exist in the alloy system. Okay, now let us see that what's a solid solution and under what conditions it gets formed. Suppose we are trying to form an alloy and we have taken two elements, X and Y, to form the alloy. Suppose X has been taken in lesser quantity and it's the solute. Y has been taken in more weight fraction, so it's the solvent. Further, suppose that X has got a phase cubic centered crystal structure and the Y, that is solvent, has got a body centered cubic crystal structure. What we do out of these two, whosoever is of the higher melting point, we melt it, and then we put the other constituent into the first constituent. We form a homogeneous liquid solution of these two elements, and in this liquid solution, all of you will appreciate that there is no crystal structure which is existing. Now after solidification, if throughout the solid that has got formed there is only one crystal structure existing, and that crystal structure is that of the solvent, that is BCC, And in that BCC crystal structure unit cell, atoms of both these constituent elements X and Y are existing, and are existing in proportion to their original weight concentrations that we had taken. The solid that has got formed is a solid solution. So what's a solid solution? Solid solution is a solution in the solid state in which atoms of the solute element and that of the solvent element share the same crystal structure. So we have written it in detail over here. See, when solute and solvent were existing separately under room temperature conditions, both of them had their own crystal structure. Importantly, the solvent had its crystal structure. And now when the solid solution has got formed, this crystal structure has not been damaged or destroyed. But then there is a difference. The difference is that where initially solvent was containing at lattice positions only atoms of element X, I should have written X over here, elements X, that was our solvent. Now it is containing elements of X also, but of Y also. And what's the proportion of the lattice positions that have been occupied by this solvent, solute and solvent? That is in proportion to the original weight concentration that had been taken. So that is why we have said solid solution is a solution in the solid state in which atoms of the solute element do not destroy or damage the crystal structure of the solvent element, but they become a part of it. In other words, solid solution is a solution in the solid state in which atoms of all the constituent elements share the same crystal structure. So see, they are sharing the same crystal structure, right? Further, solid solution, okay. I'll discuss about the type of solid solutions in the next session. But what's important for us to understand in this session is that no sooner a solid solution gets formed, you have to appreciate that the electronic structure and the size of the solvent atom and that of the solute atom is always different. Initially, they were occupying their own, they had one type of atoms were in one type of a unit cell, but here more than one type of atoms of different electronic structure of different size are now sharing a common unit cell. This leads to distortion of the unit cell. So somebody if asks you that what's the primary reason of increase in strength, increase in hardness, or improvement in properties on formation of an alloy, your answer should be, sir, solid solution strengthening. An alloy only gets formed when a solid solution gets formed in it. And when a solid solution gets formed in a solid solution, the unit cell gets distorted because of the difference in the characteristics of the solute and solvent atoms. And as the dislocations move on that, when the load is applied and when the dislocations tend to move through the unit cell, these distortions, this distorted, though I have not shown distorted over here, but actually now this unit cell has got distorted. Either it would it would protrude outside, or it would get compressed inside. But this distortion of the unit cell poses obstruction to the movement of the dislocations when the load is applied. And as the dislocations get obstructed, the properties improve. And that's the primary reason why on alloying, strengthening, or other property improvements take place. So I hope you have understood this concept of solid solutions. We'll discuss about the type of solid solutions in the next session. Thanks for watching.